presentation.
Hello? Okay, this is working. So I came to speak to you in December and gave you a kind of introduction to myself and Itasca. I'm going to give you a status report on where we are with the rock mechanics modelling and passive seismic monitoring. And I want to just kind of say that this is really a team effort. We've got a lot of experts, worldwide experts, behind a lot of this work that I'm going to show you, including a lady named Julie Shemeda, who works as a consultant to Texas Brine, and Steve Horton, who is a professor at the University of Memphis. I showed you this slide back in December. This is a conceptual model that was put together by Gary of really what we believe is happening underground. This was put together, I think, back in October, November time. And we believe that he's got it pretty much right. And what we're doing is we're filling in the details. We're saying more about the structure of this and what's actually happening underground, where all the seismic activity is located, and really trying to tell more about what's actually going on in the subsurface. And this is all going to feed into lots of other measurements, such as the ones that Don was just talking about with 3D seismics. So what we believe has happened here is that cavern 3, Oxy 3 has failed. It's a sidewall failure. It's filling up with debris. This debris top is being regularly measured, and right now it's about 500 foot from the top of the cavern. As that failure occurs, then what you do is you start fracturing the rock in a disturbed zone that goes all the way up to the surface. And that disturbed zone slowly grows and gets up to the surface and creates the sinkhole. And then you get gas coming up this disturbed zone, fluids going down, and stuff like that. This is kind of a complicated process, and we're trying to understand this. This is kind of really unique. We can't find a kind of a similar situation that's ever happened before, and we're trying to understand this, learn as we go, and examine it in detail. So there's various things that we, as I said back in December, that we currently know, and then there's a lot of work that we're putting into right now on trying to understand what we don't know. So what do we know? Well, we know the sinkhole size and shape. We know the amount of debris that's filling up the cavern. We know the size and the shape of the cavern. We can monitor the gas behavior in the near surface. And we have some information on the site geometry and the rock properties. But we don't know a number of things. We don't know the size and shape of this disturbed rock zone that comes up from the cavern up to the surface. And this is important because by understanding where that disturbed rock zone is, we'll start to understand where the gas is coming from and really understand what we can do about that gas. We don't know the behavior of that disturbed rock zone at depth, and we're trying to understand that a lot more so that we can try and predict how things will evolve over time. We don't have a good geometry of the salt dome wall. There's uncertainties on this. We're trying to understand the position of that with more certainty. We don't know what effect of this disturbed zone has on the western edge of the salt dome. And we're trying to understand more about how that's affected the salt wall. And we're trying to get a better grip on the rock properties through these sedimentary layers. So there's a lot of activity going on site to take measurements, to try and get more scientific data that can be fed into our numerical models, our understanding of the behavior of everything that's going on in the subsurface. I showed you this initial study that we performed back in December, looking at the statistical analysis of that structure and trying to work out what the greatest dimensions of the sinkhole would be. And everything that we've done so far is indicating that these are still good estimates. All of our current data, all of our current work are currently these are good estimates. And so I wanted to just kind of reiterate what this size is that we estimated. We estimated that the most likely diameter is around 730 feet, but there is a worst case scenario that would go up to 1,400 feet. The sinkhole depth is most likely to get to about 150 feet, but in the worst case it's around about 350 feet. So this type of analysis is important because people can plan on this and so forth. And what we're doing following that analysis is a lot of sophisticated computer modeling to try and show how this whole disturbed zone has evolved from the collapsed cavern up to the surface. This is our initial estimate of the maximum extent of that disturbed zone. At the moment, we're putting in a lot of effort to try and understand the exact structure within this. But this is the maximum dimension. And these are positions of instrumentation and wells that are being drilled and placed around this disturbed zone. As you can see, it flows out from the cavern 3 and up to the surface around the sinkhole. And what I think we're seeing now is we're actually starting to see fractures occurring in this disturbed zone at the surface. Part of a lot of activity that's happened in the last couple of months is to put in more seismic monitoring. And this is really to try and get a better grip on where there's these earthquakes that are happening underground are actually positioned. So a number of things have happened in those couple of months. First of all, the USGS stations, which were initially installed back in July, they've been decommissioned and replaced with 6 Texas brine seismic stations. These are like state-of-the-art seismic stations. I've been heavily involved in the design of this array that's gone in, and the stations are positioned around the sinkhole and the collapse zone to really try and pinpoint where this activity is occurring. Another thing that's happened is a 450-foot well has gone in above the cavern, cavern 3, and we've put in a geophone string in that well. That's going to be upgraded again next week. There's a 1,000-foot well gone in, or going in right now, that's going to give us rock mechanics properties. So this is how the rock behaves under various stresses and their physical properties. And that we will use to feed into our knowledge and our understanding and our geomechanical models that we're doing. In this well, down to 1,000 foot, is also going to be another geophone array. So 3 stations are going to go into this well and be monitoring. And then in Oxy 1, which is this well that goes down to the top of the Oxy 1 cavern, we're going to be putting in what's called a microseismic array, and I'm going to describe that in a bit more detail in a moment. And that's going to be placed about 2,500 feet upwards in the salt. This is a photograph of one of the surface seismic stations. The instrument is actually installed down a well about 80 foot underground. That's basically to lower the noise that we pick up from anything on the surface, and also to give us better coupling to the rock. So to basically get it below the bayou. The sensor is connected to some sophisticated data instrumentation, which then connects through wirelessly through to a seismic server that stores all the data, and that data can then be read by the public. Anybody can go and view the data online. And I'm going to explain some of this data in a bit more detail in a moment. So just to give you a quick introduction to the seismic activity that we're observing at Bayou Corn. First of all, I want to just mention that we now have two uses of the word seismic. We have what people term active and passive seismic. I'm an expert in passive seismic, and Don is an expert in active seismic. So active seismic really uses any man-made source to generate seismic waves that travel down through the rock and to really kind of image what's underground. Whereas passive seismic is really earthquake monitoring. It's listening to any natural sounds that are occurring within the rock. And this you would kind of relate to any kind of earthquake monitoring that you see in the news or on websites and that kind of stuff. At Bayou Corn, we're monitoring what we call micro-earthquakes. These are very small earthquakes. The largest ones can just about be felt by somebody on the surface. They're at the limit of human detection, if you like. And there were initially, back in, I guess, May, June, July, there were large enough events for some of you to feel going on. And typically we put those at what we call magnitude 2 or 3. And those events are very much smaller than kind of the earthquakes that you hear about on the news, so that's why we call them micro-earthquakes. In a moment I'll talk about microseismicity, which is even smaller than micro-earthquakes. These are very small events that we can only hear through the very sensitive instrumentation that we use. These micro-earthquakes are associated with very small rock movements on joints and fractures. Quite uniquely at Bayou Corn, we're also recording these what we call very long period events. And these, we believe, are associated with gas or fluid movements through voids and fissures. And I'll show you some waveforms in a minute that illustrate what these look like. And then all of these waveforms that I'll show you, they're available online. You can go to the University of Memphis website and you can see these waveforms and see actually what's going on yourself in the area. So this is what we call a helicorder, and this is what you will see online if you go to that website. What I'm going to do is I'm going to give you an example of the event that we had on January the 19th and talk you through that event and what I see in these helicorders, so that you can kind of start seeing and kind of get a feeling for what's going on these things.